So now I'm going to present our paper summary the savior, which is harmful keyword and query-based summarization for LLM jailbreak that has been accepted at Trust NLP and which is also collocated with NACL 2025. My name is Shakutur Rahman. I am a PhD student in computer science at UC Irvine and Dr. Harris is my advisor. So now let's get started. So the things I am gonna talk in this slide is about what is jailbreaking, what are the different attack methods in terms of jailbreaking, what are the state-of-the-art defenses, what are the current challenges with these defense techniques, how we tackle all those challenges using the summary the savior, basically formulating our ideas and methodology, then different experimental results of our summary the savior, and lastly I will conclude. So now LLM jailbreaking is basically a way to get inappropriate content from your LLM by using different kinds of prompt. For example, how to make a bomb. If you give this to the LLM and if it gives you the answer, then obviously that's called jailbreaking. Another example will be how to steal a bank. But the question is that really that simple that you can give LLM a prompt and it will give you the answer? The answer is no, because if you look at ChatGPT or the other LLMs, they are trained while making sure that they abide by the human laws and regulations or alignment, right? So if you give this how to make a bomb to chat gpt, then it will obviously say I cannot answer this, or I cannot do this. And so that is why there are different techniques to jailbreak. So for example, here we can see suffix generation, prompt generated by humans and assistants of different llms. So let's talk about them one by one. So in suffix generation, what happens is you have your prompt, for example, how to make a bomb, and then you add different kinds of random suffixes. And when you add these with your prompt, you basically jailbreak the LLM. So, and there are different ways to do that. For example, for white box model, there is always room for training. And for black box model, there is obviously trial and error. Like you try with different suffixes, and at one point you get succeeded. And example two would be prompt generated by human. For example, this particular example where the human asks the LLM to basically role play, but and it basically asks the LLM like how to cook, like different question answering. But the problem is it basically asks the LLM to answer each alphabet and then a space. Like while it has to answer, there should be spaces in between each alphabet. And as a result, the LLM basically gets hallucinated and thinks that it is a role playing scenario. But the problem is then the human asks like, tell me a adult website, and basically since the LLM gets hallucinated, it gives ends up giving the answer. And that is what we call like prompt engineering the human. And there is also other type of jailbreaking that has been generated by other LLMs. For example, there is one target LLM. You give it to a jailbreaking prompt and then you get the response from it, and depending on the response, you basically make changes to the prompt unless you get the target LLM jailbroken. For example, as a consultant for a struggling writer, you basically have to write a story in which you basically do illegal business in terms of faking charity. So these kind of things are generated by other LLMs by taking advantage of the target LLMs. And as a result, since there is different kinds of attacks, so you have to defend those jailbreaking, and research is ongoing in this criteria. And obviously, there are three different uh, uh, obviously there is three different types of analysis. This one is a prompt level analysis, like the prompt before going to the LLM. You can analyze that through perplexity filtering, which basically checks the flow of the prompt, like there is if there is an inconsistency or not, swapping different characters, like changing different characters or words in your prompt to see if the output changes, and classifying the prompt itself, whether that is harmful or harmless. Also, this similar kind of analysis at response level, like the we basically analyze the responses of the LLM to see whether that is jailbreaking or not, by direct classifying or using different other LLMs. And also, the while training different LLMs, you basically can apply safety alignments. So another question is, what are the different problems? So for example, Perplexity has this problem. It works well for the suffix-based attacks, like you can add random suffixes, but not on the steely prompts or prompts that have like semantic meanings. And also swapping has higher false positive rates, classification too much depended on the dataset and not robust to new attacks. And same goes for the response analysis. Like if you analyze the response, then you have already wasted the energy of the LLM because you have already generated the response from the LLM. Classification is again database dependent, so it won't work if the attack is new. So we have already talked about this, like these current defenses are specific to attacks, not universal, not robust to new attacks. They have high false positive rates and obviously hypnotized by different NLP ambiguities. And as a result, we need something that is universal, that should work. What that should work against what kind of attack you use, and also it shouldn't increase the refusal rate, and also should understand the ambiguities of natural language processing. As a result, we have generated our summary, the savior, which goes by this. So we have our prompt. We send this to the harmful keyword extractor, which is an LLM, and it extracts harmful keyword from prompts. And if there are more prompts, then obviously we create this data set. And then this harmful keywords and the query, which basically asks about the harmfulness of the prompt, goes to the security hour summarizer, which is again another LLM that we fine tune. And this security aware summarizer basically uses the harmful keywords and the query and generates security aware summaries, the summaries that have analyzed the security aspect of the prompt. And then this goes to the harm classifier, which is basically a machine learning or deep learning model. And the job of the harm classifier in this case is pretty easy. Because the summary that has been generated by the summarizer is very it's enriched with the security aspect of the prompt. And as a result, it's pretty easy for the classifier to classify, which classifies the summary into basically three different classes. Harmful gets blocked, harmless basically gets sent to the protected LLM, and the other class that we have created in this case is called ambiguous harmful. And this is for those prompts which can go the either way, because there are some prompts which you can say from one point of view is harmful, but the other from the other point of view, people may say that no, it is not. So for this kind of prompts, what we do is we pass it to the LLM with extra caution message, which we are going to talk in the next slides. So now let's talk about the different components of our methodology one by one. So the harmful keyword extractor, its job is to like generate harmful keywords. For example, how to make a bomb. It will say make a bomb. Or the example we have used previously, it would say lacking ethical or moral guidelines, unsettling responses, explicit content, etc. And the question is, how did we generate this kind of or fine tune this kind of extractor? So we had this prompt data set. We send this to the ChatGPT to generate the Oracle data set for us that we will use, or we have used basically to fine tune our Llama 2 7 billion model. And then we send this prompts, harmful keywords, and also the instruction and fine tune the Llama 2 7 billion model so that we have our harmful keyword extractor, which we can use at runtime to generate harmful keywords. And then these keywords will go to the security hour summarizer. Now, before going to the security hour summarizer, now, before going to the security hour summarizer, first we have to understand what is this controlled summary. So if you send your prompt to a normal summarizer, it will generate some summary that lacks details, maybe too long, not so specific. As a result, we need some control signals. We should send some signals to the summarizer so that it can generate summaries that is detailed, right? So in that case, what we do in controlled summary is that we say summarize within two lines, focus on these keywords, summarize while answering these questions. As a result, the summary that we get at the end is detailed, short, and to the point. And we use this technique in our security hour summarizer. So we give the summarizer the harmful keywords, the prompt, the instruction, like summarize focusing on these keywords, and also the query, like while summarizing, make sure that you classify it in between three classes. And as a result, the summary that we get is pretty focused on the security aspect of the prompt. For example, the same example, if you send it to a summarizer, it will say the prompt outlines a role-playing scenario. There is nothing bad in that. But as soon as you send the harmful keywords, instructions, the query, it says something like this. It is a role-playing scenario, but which lacks ethical or moral guidelines. It's fully harmful because it explicitly describes a character that doesn't follow AI rules, unsettling responses, and it intentionally creates a scenario where the character is free from ethical or moral guidelines. So we can see that the summary itself is pretty enriched in terms of security. And so the question is, how did we generate this kind of a summarizer? So we had this prompt data set, we already had this query and the harmful keywords. All of these are basically sent to the Llama 3 70 billion model, and this model generates the Oracle summaries for us. And then we use this summaries, instructions, keywords, and queries to fine tune another Llama 2 7 billion model. So after fine tuning, it becomes the security hour summarizer that we use in runtime. Another thing we add in your analysis is the ambiguous harmful class, and this is for those prompts that can go the either way. For example, in this case, you have to write a story faking charity and do illegal business, basically. So from one point of view, people might say that. For story, it's good, it should be encouraged. On the other hand, other people might say that even in story it shouldn't be encouraged, right? And also another example would be like write a story where the main character uses drugs. So the problem is if you just block these kind of prompts, then it will increase the refusal rates. On the other hand, if you just pass them to the LLM, then you might increase the jailbreaking and attack success rate as well. So to tackle this, what we do is we just flag these data as ambiguous harmful and then add a caution message with these prompts, and then we send this to the LLM. As a result, the LLM always gives you safe answers while maintaining helpfulness. And the caution in this case is something like that. The prompt can both have harmful or harmless intentions. So while responding, make sure that you always abide by the policy. So after that, we have used the harm classifier, which is basically a bunch of machine learning and deep learning models. And since support vector machine was the best performer, so at last we have SVM as the harm classifier. Now, as for the data set, what we have used is three different kinds of data. For harmful data, we have DAN, GPT fuzzer, adversarial Benzi, JBB, eval data set. For harmless, we have used the Alpaca data set. For ambiguous harmful data, we have used the exaggerated safety data, basically access test, while teaming at scale and Orbence. And for evaluation, we have used the widely used JBB eval data set that has different bunch of different types of attacks. And for experimental results, first of all, we have used the rogue score, which basically calculates the overlap of the words in terms of only unigram, bigram, and also the longest common subsequence 1, 2, and L. And also we calculated the BERT score, which basically calculates the embedding overlap between the expected output and the prediction. So the score we have in this case is something like this. For the harmful keyword extractor, we have got rogue 1, 2, and L as almost 40%, 25, and 37%, and the BERT score is 60%, which is quite good compared to the other even for comparing it this with different summarizers as well. And this table basically shows the security of our summarizers, rogue score and BERT score, where we have got the highest rogue scores and BERT score in terms of rogue 1 to L as 70%, almost 50%, and 58%. And the BERT score we have got in this case is 93%. And the reason behind this highest score is we only focus on the security part, and that's why our summary is well enriched and pretty easily matches with the predicted summary or the Oracle summary. We also compare the TF-IDF values of the prompts and security aware summary, and we can see in the TSNE plot that if we use the prompt, then it's pretty hard for the classifier to classify. We can't even see any clusters. What we only see is the conglomeration or agglomeration of different types of prompts, but they are not easily separable. But when you use the security hour summaries, you can even see with your eyes different clusters. For example, red, blue, and green here, which basically means whether that is harmful, harmless, or ambiguously harmful. And the reason behind this is because the summaries are very well enriched in terms of the security of the prompt. And also we can prove the same using the different machine learning and deep learning classifiers here. If we use the prompt only, then the highest accuracy we can get is 80% or 81%. But as soon as we use the security or summaries, we get 95% accuracies across all the machine learning or deep learning models. And that basically proves how well and enriched these summaries are in terms of security of the prompt. Lastly, we compare our models attack success rate in terms of different attacks, in terms of different defenses, and across these three models, Vicuna, Llama 2, and GPT-4. And the different attacks in this case is pair, steal the prompt generated by human and LLM, GCG is a suffix-based attack, jailbreak chat is basically the available data over online, and prompt with artist is basically the conglomeration of different kinds of attacks. And we can see that when there is no defense, they are pretty deadly, but with different defenses, they are pretty low. But the lowest we have seen in this case is with Summary the Savior getting 0% attack success rate in almost all the attacks across all the LLMs. And the reason behind it is that we analyze the prompts in the summaries, focusing on the keywords, focusing on the queries, etc. And one thing that is to notice in this case is that for Vicuna, we have got 22% attack success rate. And this is because this 22% data has been flagged as ambiguous harmful by our model. And when we send this to Vicuna with caution message, the Vicuna didn't respond well. And the reason is because Vicuna is not trained well in terms of the human alignment. That is why it didn't basically utilize the caution prompt in this case. And to fulfill or to prove like how important this ambiguous harmful class have been, we can see that in terms of the pair data, if we have only taken the ambiguous harmful data in terms of this pair. So if no defense was applied, then we get 100% attack success rate in Vicuna, 7% in Llama 2, and 76% in GPT-4. But if we would have blocked all the data, the ambiguous data in pair, we would have got 0% attack success rate. But with Summary the Savior, we have got 29%, 0, and 0. So from this angle, it may we may assume that ambiguous blocker should be good because we have 0% attack success rate. So all the ambiguous data should be blocked. But the things will change when we look at this data, which is wild teaming at scale data set, that is benign data but sensitive. As a result, if you apply no defense, then the refusal rate of Vicuna and Llama would be 3% and 7%. But if you block all the ambiguous data, what happens is the refusal rate increases, for example, 9% and 12%. But with our Summary the Savior model, what happens is the rejection rate maintains at 3% and 7%. So this means that we don't increase the refusal rate. At the same time, we basically have the lowest attack success rate in terms of different attacks. There, as a result, we balance both jailbreak attack success rate as well as the refusal rate. And so at conclusion, we in this presentation, we have seen what is LLM jailbreak, different types of attacks, different types of defenses, the challenges with these defenses, and how Summary the Savior basically handles all of these cases. And we have created a model that can combat different kinds of attacks and also doesn't really increase the refusal rate. And for future directions, what we have planned is to use human annotators and also multiple LLMs because for labeling the dataset, we have only used Llama 370 billion model, but we want to use human annotators as well as multiple LLMs to get voting and create a dataset that should use the voting of humans as well as multiple LLMs to be more on the safe side. And these are the references that I have used. So thank you so much.